There we go. That's good. All right. Good morning, everybody. So in this session, I want to talk about some lessons learned at Basho over the last year and a half, 2 years, in a journey we took, as it says here, lessons learned from connecting our database, which is Riak, to Spark. There's a fair amount to cover, so I'll dive right into the story. So it starts with an equation, right? Start with NoSQL, and you add in our case, it's a key value, right? So we're going to talk about the key value store because that's our flavor. But you add in Spark, and as you all know, most folks here have seen, the results of that equation are mixed, right? Sometimes it works, sometimes it doesn't, sometimes it works great, sometimes it's terrible. And so I want to talk about what we learned as we were building a connector between Riak and Spark, and overall how to turn this unhappy face into a smiley face, right? So we want to know, turn that frown upside down. And what we did, building this connector, our lessons were these 5 things. So, and this will be the crux of my talk. One is parallelize. So parallelize wherever possible, right? This is a fundamental Spark rule. Map smarting, by this I mean the idea of once you've parallelized, how do you map the data smartly as you're bringing it from a NoSQL store over to Spark itself? The third one I think of as the performance tuning piece, right? How do we do this as quickly and efficiently as possible? And then the last 2 are about kind of being flexible about what languages you use and how you do that, and then simplifying the actual deployment and integration. So just to level set, so we're all on the same page, right? So Riak, which we at Basho make, it's a NoSQL key value data store modeled after the Amazon Dynamo paper, widely used in projects that need high scale, high availability, simplicity of management. Been around since 2009, open source, you can download off of GitHub. And then, like many vendors, we have a enterprise edition which does multi-data center replication and so on. So that's what we're talking about. And we started to see, and this journey for us started with a lot of our customers asking for things like IoT use cases, time series, metrics, and analytics. So these all fit in, and we thought, well, why don't we do 2 things? This led to us, A, building a new product, Riak TS, so that's a time series database. And then the other piece of that is building a connector, this Spark-Riak connector, which again will be the crux of this talk. And if you look at it and you think about the difference between the 2 of use cases for key value store and a time series store, key value is great for high volume, million transactions around user data, profile data, lots of reads and writes of small amounts of data at high volume, right? And for us, we've built that on Riak Core, and we took that same Riak Core and then wrote a new time series database around that, which we launched this year, right? And then, again, that's oriented towards the streaming use cases, IoT devices, and metrics. And a couple of things that played into the architectural decisions that we had to make and thinking about the trade-offs of how to optimize this NoSQL world and Spark world were around, and some of these play in. So DDL, so our time series product supports ideas like create table, right? So you have more of those SQL and structured semantics. The second part is you can then say, oh, I can do select, and I can do aggregations, and I can do filtering. And then underneath the covers, architecturally, it's designed to be able to do fast bulk writes as that data comes streaming in, and then the ability to be able to query in many different ways, but in particular, and again, this plays into Spark, right? Which is I want to do it based on often a time series quanta. Give me data between this range. So that's the first part of the setup. And to give you an example of what somebody using that, say what the time series product's used for, I don't know if any of you are familiar with this idea of Formula E racing. It's kind of the new thing in the Formula race circuit where they're all electronic cars and they go crazy 0 to 103 seconds and don't go on city streets. But a company called IntelliCore took Riak TS and built a real-time application underneath the covers to take all the telemetry, all the data coming in from those race cars, and then it's used by those race teams, and then they can broadcast that with analytics and effectively near real time. So it's a pretty cool use case. And here's an example of what you might see in a screenshot from that app, right? So you can sort of be there in the race car and be on your mobile device and get a sense of that. So that's a good time series use case, right? That's sort of linear data coming in. Then the second thing we did was to then say, okay, great, let's now connect that to other applications for data pipelines. Of course, Spark is a natural candidate. So about a year ago, we released the first version of a connector between Spark and Riak. And then the current version, 1.6, was released a few weeks ago last month. And it's a Scala app. And supports currently Spark 1.6, but we're working on 2.0, and that'll be coming up. And you can download that now if you feel so inclined. Those three use cases, this is really what we want to design it for. And as I talk about these lessons, we're thinking about those three cases, right? I want to be able to read, pull that data into Spark. Sometimes I want to write that data back out, some of those intermediate results, so I can use a NoSQL, key value or time series data as an output. And then again, in this case, as a sink for the streaming coming in. The lessons that I'll talk about are also built on other connectors that we've built. So the Solar, running it on Mesos, and then using Redis as a cache. So that first lesson, parallelize whenever possible. No stranger to anybody in this room in terms of that's how Spark wants to work, right? So I'll show you through, walk you through a couple of architectural design decisions and use cases that we went through. So here, two clusters, right? On the left-hand side, you have your NoSQL cluster. On the right-hand side, you have a Spark cluster. And the operative question is, how am I going to take large volumes of data as quickly and as efficiently from one to the other, right? Whether it's co-located or whether in different clusters, whatever that case may be, how are you going to do it as efficiently as possible? So if you think about a key value store, right, it naturally wants to do gets, right? You have that key, you want to do the lookup, works great. So why don't we go through there? The workers, you're going to have the workers come across and say, I'm going to do a get, I know what keys I want, I'm going to get some more, I'm going to get some more, I'm going to get some more. And as you can see, what starts to happen is that there's a whole boatload of gets going across the cluster, and it turns red, right? You're not happy on the Spark side. And I would call that lesson 1A, right? Too many gets makes Spark unhappy, right? So too much work on the Spark side, the workers will do it. It's not that this won't work, right? This isn't optimizing. So another idea is, you might think about is, well, okay, I'll use secondary indexes to do this, right? Again, Riak, most NoSQL stores will support some flavor of secondary index. So the first step there is the worker goes across, and the Spark worker says, okay, reach over to a coordinating node, and Riak in the Dynamo architecture is masterless, right? So it could have gone to any of those. And that coordinating node then says, okay, I'll do that work. I'll go gather up that data, and then I'll send it back over to Spark. So that's what happens. And then you get the second one. So another Spark worker goes off and does the same thing. And this could be happening in parallel. And another one does it, right? And that's the way that model is going to work. And lo and behold, no surprise, what's happened is it's turned red and unhappy on the Riak side, right? Because now the NoSQL cluster is doing a lot more work because he's now being asked to go gather up all that data effectively on its own. And those lines coming over from Spark over to the cluster, well, they're not really doing that much work while all that work's going on. So I would call that lesson 1B, right? The too many 2i queries makes Riak unhappy, right? So now we've effectively moved the unhappy face over to the data cluster. That's not good. So the solution in our case was to think about splitting the difference and having both of them try and do the most amount of work as possible. And then at net with less work altogether. So the first step is that the Spark worker will say, I'm going to go over and I'm going to get something called a coverage plan. And what it gets back is a location. It's a list of where, so whatever query I specified, I'm going to get back a list that tells me where over in the Riak cluster that data is located. right? And again, this is happening with the connector that we built. So it's not that the user's Spark app has to worry about these details. It simply said, this is what I want, get it for me. So it comes back with that coverage plan, that list. And then that master, that cluster manager, driver, sends that over to other Spark workers in the cluster on the Spark side and says, okay, here's the list. And it's partitioned it, right? So it's thought about how am I going to partition that for the workers. And then when it comes back, the worker can say, oh, great, we can all get that data in parallel, right? So we've taken a bit of that two sets of work, the two failed scenarios up above, with too much on the Spark side and too much on the Riak side, and split the difference. And a lot of that's tunable. So you could say, well, I want to have a minimum number of partitions or a maximum number of partitions, or I want to be able to say, as I'm pulling that data across, how many fetches to do and what should be in a fetch, right? So how to tune that at that particular level. And what you wind up with, a much happier cluster, right? So then it sort of says parallelization, which is our cluster plan, right? Where that data is located, and the parallelization, parallel extract, as we call it, everybody's happy, right? So that, for us, was thinking about how you're going to optimize that relationship between those two clusters and do it as efficiently as possible. I think that was, for us, a very good first lesson. The second lesson is, great, now we've kind of answered to some extent how to, as efficiently as possible, pull that data across. But once it's there, how am I going to, as efficiently as possible, pull that data back up, right? So, again, on the Riak side, whatever NoSQL side you have, you're going to have, in this case, key value blobs, as well as time series data. But I really would prefer to have that farther up the stack on the Spark side, right? So I can start with RDDs, or I can have DataFrames, or ideally have data sets. And again, whatever comes into your key value cluster could be anything from JSON to binary blobs, whatever, right? How am I going to do that? And I'm going to bring that back as I'm pulling it up into Spark world and make that look as native and as flexible and as usable on the Spark side. And one bit of background to make sure we're sort of all on the same page, right? Everybody here understands key value store. In the Riak flavor of that, it's grouped into what we call sort of a virtual namespace. It's a bucket, right? So a virtual namespace is a bucket. In this case, I have some arbitrary key value data, so I call it miscellaneous bucket. And then buckets can have their own properties where I want to say, here's my replication factor, here's my quorum, here's my consistency values, and you assign those attributes to each bucket. So here's the process, right? I'm going to say I want to specify the bucket, and I want to load that data, and I'm going to get back an RDD. And so to show you a bit more code here I have a new namespace where I've said, I should have said misc bucket here. I pull that back. So I specified what bucket I want to get. And then really the next step is I say, Riak bucket as part of the Spark context, query all. And so this says, give me everything in that bucket back. And lo and behold, then I have an RDD. And in this case, for us, it's a Riak RDD, but it's effectively transparent, right? We've subclassed our RDD. We create our own DD. You could have pulled it different ways, right? You could have said, I want to do this by key, so I could specify Alice, Bob, and Charlie. I could have done it by a 2i indexed range between two numerical ranges. Or I could have said, another 2i index, give me this month and that month, right? So there's just different ways to get that data back. But once I have it back, I have RDDs and I can work with it. And we looked at that and said, well, that's fine, but again, you're still working at a sort of opaque level. I mean, RDDs, again, we can do a lot with those, but let's pull it up a bit. So how do we get data frames? It turns out that a lot of use cases for key value store, certainly in Riak, customers are storing JSON data in there. So because it's JSON data, you can then think about, okay, we can tell Spark what this looks like and how that data is structured, and then we can get back data that looks more like data frames, right? Now we're cooking with data frames. Here's what that code looks like. And you can see it's not that different than what we did before, but the really difference there is that second step where we're going to do a case class, and we're going to say, here's what my data looks like. Here's what that JSON structured like. In this case, I have an ID, a name, and an age, right? So I take those, say, this is what it looks like. So when I get that RDD back, that very last statement in the load data, as you can see, we do a 2DF, and now you've got a data frame to work with, right? So now that's being a bit smarter about how to use that data. That's the key value side. But as I told you earlier, we also have a time series side. So what do you do when the data is a bit more structured? Well, in this case, it is structured. So what can we leverage? And so we're going to leverage is automatic schema discovery, right? So automatic schema discovery is going to allow us, in this case, to get data frames back and get rid of that second step, right? Here's what that looked like in code. And code-wise, there's a couple of things of note here. So I'm showing you sort of how you would specify the cluster, right? So we're saying where to go get that data. I could have given a list of nodes, but again, because it's master list, here we'll start off with one. And then there's a format, and I'll talk about that in a second. You load it, you select it, I say, what columns do I want, right? And then I can also apply a filter, right? Because it's already structured. And then I'm off and running, right? I can do whatever I want. So I can do the where clause, I can do the aggregations. So that's, again, a better level in many use cases for Spark side to pull that back up above an RDD. And for those of you who might be interested in doing this yourself, say you want to point to a different data source, we implemented the Spark data source API. And when you do that, that's sort of that lower level that says, well, I can either do it for file systems, I can do it for other external data sources. And I think it has 3 interfaces that you implement. We did 2 of them. But that allows us to do all the magic underneath the covers here. So that's really where all that voodoo's happening. The third lesson, so now we've gotten the data over, we've gotten it up, but we thought about how am I going to do this as efficiently as possible? So that's the idea of I'm going to optimize all the layers, right? In particular, let's think about the transport layer. A lot of the libraries that we all use in Spark and NoSQL land often will have at least these 2 interfaces, right? You'll have an HTTP interface, and you'll have some binary, in this case, protocol buffer interface. One oriented towards performance, one oriented towards flexibility, right? Not unusual. Now, in our case, and so those who don't know protocol buffers, right? This is Google started this in 2009 or so. Serialization format. You define your IDC, it makes RPC calls, and you have a wire transport, right? And you don't have to worry about that in Riak and a lot of other applications because it's that ugly bits are taken care of underneath the covers by the client SDK, right? So you don't have to worry about that. But it matters here because we're thinking about, well, wait a minute, how much faster is it? Why would I want to do it one way versus the other? And and I invite you to keep in mind that it's a noticeable difference, right? On most of the tests that we've done, it's a 3x difference if you're using protocol buffers versus HTTP. So it means something to use one versus the other. And if I go back to this diagram, all that transfer that I showed you was happening between the Spark connector that's deployed to the Spark cluster, or the Riak Spark connector, and the Riak side. That's all happening primarily on protocol buffers, right? So we're trying to make that layer as optimized as possible and as fast as possible. So we looked at that, that's fine. And we thought, well, wait a minute, we looked at some of the usage patterns, and it turns out some of them we could make faster. So how are you going to make it faster? So we have an optimized binary format that's faster than, in our use case, than the protocol buffers. And we're primarily an Erlang shop, so underneath the covers, it's actually using, those of you who know Erlang, we're using Erlang's term to binary and binary to term underneath the covers. Again, you as an application developer, we don't want to expose that to them, so the Spark-Riak connector does that under the covers. And it also makes that selection on the fly. So thinking about how am I going to optimize performance, but it doesn't necessarily, out of the set of API calls that you as a developer might want to make connecting Spark to this NoSQL cluster, all of them are not the same in terms of what you're trying to do. So I'll give you an example. For us, bulk time series operations, these things like fetch, query, store, where they're getting a larger chunk of data, those are the ones in which underneath the covers, the connector will make that decision on the fly. It says, oh, this guy's trying to make a bulk query. I'm going to do this in the optimized binary. I'm going to make a term to binary call and take care of that. So that's the wire format, right? And then you go, well, that's great. And what does that mean from a performance perspective? And for us, that's another 30 to 50%, right? So you've gone from HTTP to protocol buffers, which gains you up to like a 3x performance. And you could take that again and optimize that a bit further for a certain set of API calls. And that's some of the transport level stuff. But there's a couple other optimizations that we thought about between, again, sort of making these two worlds work as happily together as possible. One of them I showed you before, but I didn't necessarily mention what was going on underneath the covers, which is that Riak KV supports this idea of a full bucket read. So rather than going and specifying the individual keys as gets, I can say, as I showed you in that example, there was a call there that said query all. So query all was a somewhat newer Riak operation that says, I can get you everything in that bucket, right? Because then I can just pull that across, certainly in Spark land, and say, I'll deal with that over here. Get me that set of data because I've already grouped it in a way that meant something for my application, right? That's why I put it in a bucket. So I'm going to say, give me everything in that bucket, and I'll take that over here, Spark, thank you very much, and I'll work with it over here. A different flavor of that, sort of going back over to the time series, with somewhat more structure, as you're thinking about sort of joining these two worlds. Time series has, this, in particular, this idea of a quanta, right? It's that, how have I grouped the data? And I sort of did this as I was doing my data modeling. And I wanted to sort of group it by minute, hour, up to a day. You probably don't want to do more than that, but somewhere in those time ranges. Because underneath the covers, Riak's going to then try and take that and distribute it across the cluster based upon those time ranges. So as the data is coming in, we're going to plop it down in the cluster on the same node or the same virtual node to make it as efficient on the write and also on the read. And sort of what that looks like, here's an example, right? So you're doing a put. On the left-hand side, that's a classic key value put, right? Again, Riak's a cluster, a masterless architecture. So it comes in, it's going to do a consistent hash on that data and then spread it around the ring, spread it around the nodes. But when it looks at the composite key for a time series put, it's going to say, wait, am I still in the same quanta I was before? Quantas for this on this composite key based upon that go here. And I'm going to keep going to that same spot as long as I can, as long as I'm within that. And therefore, A, the writes become more efficient for that scenario. And then if I'm doing a get, those gets will be more efficient as well, right? So if I'm pulling this back to Spark, and I'm saying, as I often do, get me the time for yesterday or the last hour, that's going to be a lot more efficient and a lot more optimized as a way to pull that data back out. As a for instance, here's how you might define a weather table in Riak TS. As you can see, it looks pretty much like a standard create table, except the difference here is in definition of that primary key, right? So as you can see where it says primary key and that quantum on the right-hand side, that quantum there says, I'm going to do it based upon the time field, and it's going to be a 2-hour quantum. So therefore, as that data comes in to write in Riak, I'm going to try and group that by locality on the same node, on the same V node, based upon that time quanta. And again, that's sort of the tunable key to performance. And then when I want to pull it out, so now we're again talking about on the Spark side, all I have to do is I could say, I could use regular SQL command. I can say, select star from weather, where city equals Brussels, and give it some time quanta, right? And that may span multiple time quanta, but again, underneath the covers, that connector and on the server side, they're going to figure out, okay, what's the most efficient way to get that and not have to go to as many nodes as I might if I was doing a non sort of straight key value query. So that's another way. So that's sort of how we thought about both the transport layer of optimizing as well as the more structural layer in terms of the data structures within the database itself. The next idea is, the lesson for us was how to be flexible about a number of different things within what I just showed you. So part of that's being polyglot, right? These are, as you know, the favored language in the Spark world, right? Doing Java, Scala, Python. And this doesn't necessarily come for free, so we had to do a little bit of tweaking on our side to make support for that work. But that was really important, and it really paid off already in a relatively short period of time in terms of adoption and flexibility, again, for supporting a bunch of different use cases, whether somebody wants to work, whether it's a Python environment from a notebook, or whether it's a Java app or a Scala app, supporting all those. But again, anybody who's building a connector, I encourage you to make sure you've tested those, because it doesn't happen for free out of the box. Here's an example of the Python flavor of that. So I'm doing the setup, right? So you'll notice at the very top, my import, I've said import Spark-Riak. I mean, I also imported PySpark itself. Again, to set it up, I'm going to say, where's my cluster? And then I'm going to integrate the two contexts, and then I'm ready to go do a read. So when I do my read, actually, I'm going to start with a write. I'm going to say, here's some data. I'm going to say, here's how to turn that data into a RDD and parallelize that, do that partitioning when you do it. And then I'm going to save it back to Riak in a bucket. And to do the read, I'm going to do some of the inverse, right? But again, you'll see that I've done, I specified the bucket name, and I've done a query all. And to highlight that, going back to lesson number 1, parallelize whenever possible, right? So there's at least 2 flavors in both directions here where we're thinking about taking advantage of that. Again, at the application layer, we haven't really, you're not worried too much about that. It's just sort of happening by voodoo. The next part of flexibility is Spark streaming. So again, here's the classic Spark streaming diagram for us. We have the Riak side. We can be a sync. And if you want to look at that in code, here's what that would look like. So again, that same connector that we built takes care of this logic. It wasn't really, this one wasn't too tough to do. But you specify the context. Those of you who, I don't know if you did the streaming flavor, right? You specify what the bucket should be. So that says, give me 1 second buckets or batches, I guess is the appropriate word. And then I pull that back, and I get D streams out of there in the streaming part, and I get those lines, and then I can filter those. And so I'm kind of off and running with Spark streaming, and then I can save that back out. And the last part about flexibility I just want to sort of hit on real quick, for both Riak and most of your NoSQL stores, you have these options, right? A lot of our customers do different flavors of these. And you can do that on the Spark side. And I'm sort of showing you one example here where on the left-hand side, they're co-located, right? I've decided, well, it's more important to me to have that data co-located, so I'm minimizing the amount of transfer of data across nodes because they're running the same boxes. On the right-hand side, I said, no, I'm going to put these on separate boxes because basically these are both resource hungry. And so, as you know, Spark wants lots of memory, lots of CPU to be able to do its work. So I think more often than not, you're going to have the happy face if you're doing the flavor on the right. It doesn't mean you can't do the one on the left. They both work fine, depending on your workload. Speaking of deployment modes, Riak, we have a Mesos, what we call the Riak Mesos framework. So you can download that, and if you want to do that sort of deployment mode, have at it. But I think it's another level of our lesson number 4 here, which is to be flexible. And last but not least, this is the idea of simplification. This is probably the least technical of all the lessons for us. But the idea is, how am I going to minimize friction? And minimizing friction, one idea is think about where am I going to deploy that connector itself. Because it's kind of nice if I could just go put this, and what we did is we put this up on sparkpackages.org. So when you want to deploy this and run this in your environment as a developer, the crux of this is really this call here where I say, I'm running Spark shell, and I say -- packages. I specify the Spark-Riak connector, and voila, I'm off and running, right? So it saves me a bunch of this sort of niggly work about getting that to work. We also, between Basho and Databricks, sort of have, we put a notebook up on databricks.com, which allows you to sort of walk through that. So the code's up there, classic notebook format, but it's a great way to get started. So I think that was another part of the simplification. And last but not least, it's dirty work for developers, but for the organization, for us, it was really important to have a good, enough documentation to make sure that all worked. One bonus lesson. The bonus lesson is don't die. As you know, in these environments, stuff happens, nodes die. So if a Riak node dies, the Spark-Riak connector will recognize that, and we'll go get what we call an alternative coverage plan, and it'll figure out, okay, well, that node's dead. Let's go figure out where else we can get that data for that query. And for us, building on top of this, we're going to support Spark 2.0, data sets, and streaming. That's coming down the pipeline. And so back to the question, right? So how do you take these two and make them happy, from the unhappy face to the happy face? I think these are the 5 lessons that I hope we can walk away with. And I see that we're out of time. So thank you very much. Oh, we have a booth downstairs, so come by, more questions. You're happy to come down and see. We have a little racetrack down there.